Hello and welcome to Calculus 2, section 7.4 on trigonometric substitution. So some of the integrals are solved by u substitution in Calculus 1. Then you have that integration by parts, which is actually sort of u substitution as well. And now we're going to have trig substitution. So we are going to take a problem which has x's and dx's and so on, and transform that into trig functions like sine theta, secant theta, and so on, with d theta at the end, to actually make the problem possible to solve. Are we making it easier? Well, actually we're making it possible. So the story of easy or hard really doesn't stick, right, in this case. Now, in the textbook you have three formulas, three situations when those formulas apply, and then you go and deal with that. I do things a little bit different. What I'd like to do is use the Pythagorean theorem to set up so you can actually avoid memorizing those formulas and situations. You just go and do every problem the same way. So the method is, why is this blue? So we have a right triangle with angle theta, and we know that this side is called the opposite, adjacent. We don't need the plus minus for square root because plus minus. Now, we're just going to observe for a second these formulas and realize, if you are good with that, we can go and learn the method for trig substitution, and this procedure, as I said, fits every single situation, every single problem. So there are no reason to memorize different situations and different formulas. You just learn this one method. The homework for this section contains in the neighborhood of 7,000 problems. It's a really good section to practice. I'm going to show this to you. So it's like 40 problems just on page 1 of homework. And one method is good enough for all of them. So I'm just going to pick random problems from this section. And once you figure out this method, I will suggest that when you get home, you try the exercises that are done in the textbook, in the text, using this method rather than what they have. And then you will also be able to see the solution they have to know that you did that correctly using the other method. Please note that pretty much every single one of these problems has a square root in it. And those that do not have square root most likely have a 3/2 exponent or a 5/2 exponent, right? The square root should be really ringing a bell from the Pythagorean theorem you've seen, right? So we're going to use that Pythagorean theorem to assign these values under the square root as sides of the triangle, and then just read the trig off of the triangle as opposite over hypotenuse or whatever we get. So few of these examples will not have that, like a 43 has 81 minus x squared, everything squared. But we can actually fix that. That's not a big deal. So let's go and do a few of these examples, and then make sense out of all of this. So this is what we need, and now let's go and work on whatever of these problems. Say, I don't know, give me a problem 7 through 16. Seven through 16, please. 8. All right. Thank you. Wow. All right. Look out of all numbers that you could have picked.
I was only choosing the ones that were lower than 7.
I said 7 and 13.
I know, and I wanted to see how quickly you would catch it.
I teach math. So it's dx over 9 squared, and it has 3 halves here, which is okay because we know that it has a half, which is a square root. Now, what do I have? I have a minus sign. Since I have a negative there, great. Since I have negative, immediately means that square root of 9 equals 3 is hypotenuse. If you don't believe me, just look at these two formulas. So if there is a negative underneath, c squared is always first. That means that the c, which is hypotenuse, is 3. Can we all make that connection very quickly? Yeah, I'll even get up, okay? That's like 3 calories to do this. I'm all about conserving energy, okay? If I have to get up like more than 5 times, you owe me a burger. So, it's okay, split between like 10 people is $1. Minus sign, minus sign, minus sign, but these are the formulas you know, and it's always a c and a c, and a c is hypotenuse. Therefore, this 9 must be hypotenuse, right? And then, this x, you can put anywhere you want. You can put in the, on any of the legs, because these formulas are symmetric, as you can see, right? So it's either minus 1 or minus the other. It doesn't matter. So this is the core. Once you sort that out, the rest is just a procedure that you go through mechanically. That's technically what it is. So right now, I'm going to draw the triangle for this problem. So I have my triangle here, and I know that 3 is hypotenuse, and I can put this x anywhere. So I can put x there, or I can put x in the denominator, on the bottom, whatever, doesn't matter. Now, if these are the sides that we picked, then square root, this side must be square root of 9 minus x squared by Pythagorean theorem. It has to be. Because this would be the side A, and then A is c squared minus b squared, right? So there you go. The trick to the method is to write sets of two equations, right? Both using the side which has a number in it. You see how we'll have a red set that includes 3 and a blue set which also includes 3. So you can't have this. You cannot have that, because that does not include the side that has a 3. So this is all you have to learn. From here, everything else is a steady flow. So if you can connect this to your previous pre-calc course, and you know how to write the trig functions given sides, you're done. So let's go. What's the red stuff? Well, red stuff is hypotenuse and opposite. So that's going to be sine theta. So sine theta is equal to opposite over hypotenuse, so x over 3. From there, x is equal to 3 sine theta. And remember, you will have to swap the dx as well. So take the derivative immediately. dx is 3 cosine theta d theta. We got a lot of stuff out of this one trig equation. We have a substitution for x, and we have a substitution for dx. Very good effort. Nice. You will always be able to solve for x in one of the two sets, either blue or red. Now, I switch to blue. What do I have for blue? Well, I have adjacent and hypotenuse, and that is very good. Cosine theta, and the cosine theta is going to be the square root of 9 minus x squared. Ugh. I think my battery is dying in this, I have to change it. 9 minus x squared divided by 3. From here, I can solve that the square root of 9 minus x squared is equal to 3 cosine theta. Now you just swap things in and you're done. What do I have? The integral of dx of 9 minus x squared to the 3/2. This is equal to the integral of dx over 9 minus x squared. You can say that's a square root, which is a half, and you still have a cube on the outside. So you just plug in values what they are. Integral of, you have dx is 3 cosine theta on top. In denominator, your square root is given by 3 cosine theta, and you need to cube the whole deal. Oh, I forgot the d theta on top. Oops. Dx was 3 cosine theta d theta. That's not there for decoration. We need it. So now when you simplify this, while you apply the cube, you have 3 cosine theta d theta in the numerator, and denominator is 27 cosine cubed theta. Cancel, kick the constant outside, so that's 1 over 9 outside, and inside you are left with d theta over cosine squared theta. What's 1 over cosine squared? Yeah, squared, exactly. So integral of secant squared theta d theta. Now, what is the integral of secant squared? Very good. So that's 1 over 9 tangent theta, oh no, plus c, because we have a definite integral. We had 0 to 3/2. Now, here is the reason why I don't like what is done in the book, the way they do it. Because you are supposed to memorize formula from the book. You don't have this triangle. You don't draw this with the method in the book. So, the method in the book tells you to remember when you have a minus to use this formula, and then you have to plug in and do a ton of algebra, and yeah, sure, you are eventually going to get through all of this with the book method and get here at the end. How do you convert back into x? Right? In my case, it's a joke, because all I need to do is to go and read what tangent is on this graph. And the tangent is opposite over hypotenuse, which is x over the square root. It's done like this to convert it back. Remember, anytime you have to do substitution, you have to go back to your original variable. You did that in u sub, you did that in all of the other ones, right? So you will have to do a lot more work to go back, right, if you don't have the triangle. It's possible, but it's a lot of work. So all I need to do now is to say this is x over square root of 9 minus x squared, and then I have 0 and 3/2 here, which is equal to some number. There, perfect. Yeah, it's called quick computing. You should be able to plug in 3/2 and a 0 and then come up with whatever decimal is there. So the entire method for every single problem in this section is going to be this. You take a look under the radical. Do you have plus or minus? If you have plus, it's two legs. Those two values, square roots, are put on legs. And then the hypotenuse would be the square root. If you have minus, the first value you have is going to be hypotenuse. And then the other one is going to be either one of the two legs. It doesn't matter. And then you go from there. I got it. Anyway, let's do another example. Every single problem done the same way. I was about to say anything from 17 to 25. You think so? Anything from 17 to 25? Holy nightmare.
13.
Thank you. What is your name?
Ben.
Thank you, Ben. Holy nightmare, people. 19. Is pretty much the same problem we did. Is the same problem we did. Sorry. Look. What 19 did is swap 1 and 9, and that's it. The same problem. So let's pick anything else.
Is one with a positive? Like a 9 plus 21 in the denominator?
21 it is. Thank you. 21. Oh, we're going to do 5 or 6 of these. It's going to be... You should do stuff till it becomes boring. And then you do one more, and you're good. It says dx over x squared square root of x squared plus 9. Perfect. That's a plus there. Plus means a, let's say, equals x, and b equals 3. That's what it means, because you have two legs. If you go back to our Pythagorean theorem that you learned in your whatever grade school, you have that with the plus it's a and b, those are the legs, and that's that. Great. So, we draw the triangle. Theta, a, well, it doesn't matter where you put them. There we go. And this is going to be immediately x squared plus 9. Because Pythagorean theorem, x squared plus 3 squared is that. Remember to circle towards the number. So we circle this way. Ooh, this is going to be a cosecant cotangent pair. You like cosecant cotangent? No? Why? Is cosecant cotangent the same as secant tangent? It's a pair. The cool thing about this method is you can actually avoid it. All you need to do is to swap 3 and x, their legs. So if we swap 3 and x, it's going to become tangent secant pair. But since you said that you don't like cotangent cosecant, we're going to do cotangent cosecant. Yeah. If you ever take my class, if you tell me I don't like yellow paper, you get yellow paper. I don't like pink paper, you get the pink paper. Right? As some poor students from my statistics class can confirm. So we're going to do cosecant cotangent pair. We're taking a look at the red formulas, and we see that we have opposite and opposite and hypotenuse, right? Opposite and hypotenuse are giving sine. So when we write sine theta, we get 3 over square root of x squared plus 9. And you have to solve for square root because you are subbing for that, right? Well, square root goes out. It becomes square root of x squared plus 9. And this becomes 3 over sine theta. And that is 3 cosecant theta. So now we have that the square root gets replaced by 3 cosecant theta. Blue set of sides is going to be, say, tangent, because it is opposite over adjacent. So you write tangent theta, and if you have tangent theta, you have 3 over x. Your job is to fish out x. So x is equal to 3 over tangent theta, which is 3 cotangent theta. Remember that you immediately need dx, the derivative. What's the derivative of cotangent? Very good. So, negative 3 cosecant squared theta d theta. Perfect. Technically, all of our substitutions landed in here. You have to sub for x squared, so that's going to be 9 cotangent squared over there. You have to sub for the square root, and you have to sub for dx. You just plug them in like little Legos. So you just have some little preliminary work, and then you plug everything in. So now our integral of dx over x squared times the square root of x squared plus 9 gets replaced by dx is negative 3 cosecant squared theta d theta. That's the numerator. I need to square the x, so that's 9 cotangent squared theta. And the square root is 3 cosecant theta. There you go. We transformed the entire integral into the trig integral, and now all we need to do is to simplify this, and we are done. We kick out negative 1 over 9. 3 and 3 cancel. And then we cancel one of the cosecants with the cosecant in denominator. So what you are left with is cosecant theta divided by the cotangent squared theta d theta. That's it. The negative is outside with the 1 over 9. Let me do a better job on that negative. Exactly. I can also zoom in for your convenience. Sure. Right there. So, yeah. Extract. All right, no problem. So now we have. So now we have to solve this mess. One of the best ways to attack a trig integral, which was your previous section 7.3, is to, if you have no clue what to do, is to try to convert everything into sines and cosines and see if you can wiggle your way through. If that's not possible, then it's going to be some of those Pythagorean identities with the sine square, cosine square, cosecant square, and so on. It will be that. And the last resort is going to be integration by parts. The list of tricks is really finite. Oh, you sub as well. Those 4 things. So I'm looking at this and I have no clue what to do. So I'm just going to try and convert everything into sines and cosines and see if anything comes up from there, right? So that work is going to be orange and on the side because I'm just scribbling, and then if it pans out, we're just going to continue in black and do it. So cosecant is 1 over sine theta, and the cotangent is going to be cosine squared theta over sine squared theta. Now, sine squared will lose one of the sines. Maybe I should use different color because blue. Complementary color. There we go. And when you solve double fraction, you have sine theta over cosine squared theta. Yes! We have a single sign in the numerator, which means we can unleash u sub upon this because you have a squared. So as long as you have the exponents of sines and cosines in denominator and a single one on top, you can use u sub. So the entire problem becomes negative 1 over 9 integral, and I have sine theta d theta over cosine squared theta, and now we unleash u sub. U equals cosine theta, du equals negative sine theta d theta. Now we're going to steal the negative from 1 over 9. So we have 1 over 9 integral du over u squared. What a roller coaster, right? Started with x's, right, and expressions, radical expressions, then moved into trig, and now we're down to rational expressions, so yay, right? Integrating this becomes negative 1 over 9, again, 1 over u plus c. Now the famous sentence is, I don't care about u, I care about the x, right? So, no, because we started with the x variable, right? And now we have a u variable. So it's not good to keep it that. We have to go back to x variable. So we convert u back into trig, then we use the triangle to go back to x, and we're done. So what do I have? Negative 1 over 9, and 1 over u is 1 over cosine theta plus c. Please don't forget to put the plus c. It's not there for decoration. We need that stuff. So just make sure every time you have a indefinite integral plus c. If it's a definite integral, you have the limits. It will be a number at the end. Bueno. 1 over cosine is? Thank you. Plus c. And now all I need to do is to go and read what that secant is from my triangle. Now, secant is hypotenuse over opposite. So that's a square root over 3. It's a square root over 3, square root of x squared plus 9, plus c, for the total of negative square root of x squared plus 9 over 27, plus c, and you just walk away. That's it, done. Welcome to Calc 2. We teach elementary algebra and the 5 line of the equations. Like, this problem is too long. I know, right? Alright, so for this problem, this is me getting up second time. Don't worry about it. We have a plus. Plus means that the two values under the radical are lengths. So x and 3. You can put them in any order you want. Now, the trick is, if you put them one way, you get secant tangent pair. If you put it the other way, you get the cosecant cotangent pair. That's what you have to be careful about. If you don't like cosecant cotangent, swap them. Then your circles will be going this way, and you will be having a secant cosecant. So maybe you can start this problem and challenge yourself at home to redo this problem, and you have to end up with the same answer because the answer is the answer, right? It's the way to get there. And key points are to understand plus and minus so that you can set up the triangle. The second key point is you will be creating the trig functions towards the side which has a number in it. So this way and this way in this case, because that's where the number is, 3. Sometimes this number is 4, 5, or whatever it is, right? And it's anywhere. You always create functions. So that number always needs to be circled twice. Once you have those equations, one of the equations will be a single x equation. That's the one you differentiate for dx. When you have a problem, you have to replace dx with expression d theta. You have to replace x squared here and the square root. So 1, 2, 3, and we actually had them all together in a box. So I could box this and call it a substitution box because that's what we used. Next example. You know what? Just pick something. $31. Okay. 31 it is. Integral square root of x squared minus 9 over x dx. Great. I have a negative, which means c is x, because the first value is always hypotenuse when you have a minus sign. And then number 9, which is 3 for the length, will go on any of the legs. Doesn't matter. Now we are going to switch it if we don't like it. So just arbitrarily put it somewhere. And we have x squared minus 9. And as I said, if we don't like it, we swap it. Now I already see we don't like it. Because when I do this pair over here, it's going to end up being 3 over x as a sine, right? Which means 3 over sine, and that's 3 cosecant, right? So we swap it. Let's do a secant pair. So put 3. That means that the square root will be here. Now I have the pair for x and the pair for square root. All right, red one. Cosine theta is equal to 3 over x. Really? 3 over x, from where x is equal to 3 secant. I gotta change the battery in this thing. 3 secant theta, and then immediately the derivative dx. Derivative of secant is very good. Secant theta tangent theta d theta. Don't forget the d theta at the end. It's not a decoration. I mean, we need it for the integral. So that's red. Now we have blue. The blue pair is going to be tangent theta. which is the square root of x squared minus 9 divided by 3. So the square root, you always solve for x and square root because that's what you're substituting, is 3 tangent theta. I have all of the equations that I need, so now we just sub. So the problem is integral square root of x squared minus 9 divided by x dx, and I have now integral, instead of the square root, I have 3 tangent theta. Instead of dx, I have 3 secant theta tangent theta d theta, everything divided by x, which is 3 secant theta. Well, stuff cancels. Kick 3 outside, and you get tangent squared theta d theta. Put $1 million on the table to see how we integrate this tangent squared. You know you can't go sine and cosine because you're going to end up with the sine squared in the numerator. You can't do u sub, right? So what do we do? I'm sorry? Ooh, that would actually murder this problem. We can't do power reduction this one. It will actually make it work. It's a good try, though. Anytime you obviously see sine squared or cosine squared, you must use power reduction formulas. Yeah, that would be a good fit there. We eliminated that already because I said you can. Guys, I show you this and I leave. All right? 7-4 is over when you figure that out. When you have your substitution, from here till the end is 7.3. And if you don't know that, right? Tough luck. So do you actually have to sit down and learn 7.3 on its own? No. Because every 7.4 problem includes 7.3, right? Because that is actually, once you get the integral, you have to use the skill from 7.3. Now, since that's really fresh in your mind, exam was just over, you're still taking the vacation from Calc 2, right? One more time. When you have a trigonometric integral, talking 7.3 here, right? A, you either go back to sines and cosines, it's going to be cheap, or use sub. If that doesn't pan out, you have the u sub within secant tangent pairing or cosecant cotangent pairing. And then the last resort, right? Well, no, that's not right. And then you have the Pythagorean identities, which is actually what solves this, because when you do the tangent squared and go into secant squared, integral of secant squared is tangent. Oh, okay. And then the last resort is probably u by parts. So those are your options for 7.3. The list is finite. You just have to sort that in your head. So let's practice these mad skills. I already told you that you have to use the identity to convert this into secant squared. What is so, well, what is the standard form in what's given?
Isn't it the sine squared plus cosine squared equals 1?
We can start there, sure. Sine squared theta plus cosine squared theta equals 1. And then you need a secant, right? And a tangent. How do you get tangent out of this? What do you divide? What do you need to divide by to get a tangent squared? By cosine. So divide by cosine squared, cosine squared, cosine squared. And there is your tangent squared theta plus 1 is equal to secant squared theta. So to replace tangent squared theta is going to be secant squared theta minus, as the Russians would say, 1, which is 1. Cool? So now you are going to replace the tangent square with this. You can integrate this and you can integrate that, and then use the triangle to sub back. Now this was 7.3. We'll have to do something a little bit more than 7.3 after the problem, because I see it says the disturbance in the time. So it's a secant squared theta minus 1, not 1 minus secant, right? D theta, which will give us 3 tangent theta minus theta plus C. And then we go and, well, we have 3 tangent theta minus 3 theta plus C. What's tangent on our square root over 3? Okay. So square root of x squared minus 9 over 3. 3's will cancel. Minus 3 times. And now for theta. Guys, you have 6 trigonometric functions. Pick one. And just do the inverse trig. So what do we have over here? We have cosine theta is 3 over x. So if cosine theta is 3 over x, then theta must be inverse cosine of 3 over x. So inverse cosine of 3 over x plus c. 3's are cancelled, so that's it. So the answer is the square root of x squared minus 9. Well, I'll write it one more time. There it is. Now you see the headache in grading this, right? There are 6 possible answers here. You can use cosine, but you can use sine or tangent or secant, right? You can use any of the 6 here with the inverse, because each one of these would have a theta when you write it down. So generally the best way is to just use the one that it's, you know, up there on top easy. Next example. Some people are disqualified to pick the next example. So those who are not disqualified, let's go.
So if the x is greater than 3, anything?
Yes, means that x is greater than 3. All the value, you can pick any x bigger than 3 and the problem will work. If you pick anything less than 3, problem will not have. The problem will not exist. Because if you think about it, over here, if you have if x is 2, 2 squared is 4, 4 minus 9 is?
Negative number.
And then square root of that is?
Possible.
It's possible, but it's imaginary. Yeah, exactly. So, it's a way to quickly identify visually that you are supposed to use. All right, what else? Anyone?
hard is it? How hard is to pick the number? 30.
Beautiful. 37. Integral of, holy nightmare, 9x squared minus 25 over x cubed dx. X bigger than 5/3. Since you asked, there we go. We'll make sure we add that. Why? Well, now you have 9x squared. It's a minus, so hypotenuse is what? What's the hypotenuse?
5.
Hypotenuse is always first when you have minus sign. What's the square root of 9x squared? Exactly. 3x. And now we have 3x there, and we have now 5. 5 could go on either one of these two. Where do we want it? Well, we want sine and cosine pairs, and we want secant tangent because it's easier than the cosecant cotangent. You have to worry about negative signs as you differentiate and integrate secants and cosecants, right? There are minus signs everywhere. But in the case of secant and tangent, you don't have to worry about negative signs. So, if we place 5 here at the adjacent, because we label where theta is, if we place this here, what do we have? We have 3x, and then over 5, that will be sine, no, that will be cosine, and then when you flip it, it's secant. So this is our square root. All right, how about you have fun with this for a little while? And then I'll kick in too. So. Alright, so does this match what you have so far for red and blue before you sub?
Yeah.
So now you just replace Lego pieces. So if you're able to get the triangle and circle towards the number, in this case 5, there's only one way to do this. So now the square root is 5 tangent theta. The x cubed is going to be 5/3 secant theta everything cubed, and the x is 5/3 secant theta tangent theta d theta. It's a long expression, but it gets simplified, right? So let's see. I have 25/3, and then I have 3 cubed over 5 cubed to kick out. Integral. I'll just kill one of the secants right away. And I have tangent squared theta over secant squared theta d theta. I hope this simplified what you guys had, right? Good. So now I have 25/125, and then, well, 9/5 integral. Tangent is going to be sine squared theta over cosine squared theta divided by 1 over cosine squared theta d theta. You should start smiling, because we are getting what? What are we? Yes, we're getting power reduction. You were craving it all night, right? You came into class, one integral tonight, must be power reduction, that's it, right? So there we go. This is what you wanted, so rejoice, right? So we have sine squared. The only way to integrate this is the power reduction formula. So you either know it or you walk away. That's technically what it is. We have 9/5 integral, and the power reduction formula is 1 minus 2 theta, very good, over 2 d theta. 2 gets kicked outside, becomes 9/10. And now we have integral of 1 minus cosine 2 theta d theta. 9/10. Integral of 1 is theta. Integral of cosine is sine, so that's going to be sine 2 theta over 2 plus c. So when we distribute 9/10, becomes 9/10 theta minus 9/20. I mean, we don't have to distribute. Well, let's leave it not distributed. Whatever. So I can just sub. What's the theta? Go up and use the inverse trig. It's inverse cosine of 5/3x. Inverse cosine of 5/3x. That's theta. Minus 1/2. Ooh. sine 2 theta. We have to expand that into 2 sine theta cosine theta. 2's are gone. We have 9 over 10 cosine inverse of 5 over 3x minus, and now you read the sine, read the cosine. Sine is going to be 5 over 3x, and cosine, we have that written, 5, no, the sine was supposed to be 5 over square root. 5 over the square root, and this one is 5 over 3x. Good. What was our square root? 9x minus 1. Who came up with this? 25. Perfect. Plus c. So we have 9 over 10 cosine 5 over 3x minus 25 over 3x square root of 9x squared minus 25 plus. These problems are awesome, right? Like for killing time and carpal tunnel, it's like amazing. Like you always have like to do this exercise before you. It's like, oh, it's going to be a trig sub. Nice. Let me warm up. You go like that for like 10 minutes. You'll be fine. Don't worry, next section is much worse. I mean, longer problems. This is still on the shorter stuff. Great. Look at that. Please, next time someone tells you, what do you know? Just work one of these on a napkin. And say, here, what do you know? Cool, huh? One method, all of the problems. So we're just going to work on one more problem, which is the oddball. And then we're going to take a break. And we'll see what we're going to do later. Sounds good? So one more problem and the lesson is over. Now I get to pick this one. And that is problem 43. We could have done 30 as well. You know, there are a few of these. How about we do 30 actually, because there's a plus in it. Because we had a lot of these that are minus. So let's do 30. See you later.
See you later.
Yeah, it's later.
We'll see you sooner than later.
81 plus x squared. So x squared divided by 81 plus x squared squared dx. No square roots. No half exponents. Right? Can we use trig sub? And the answer is yes. Can anyone tell me how I can just push once on 8 and it's gone. Right? Look at that. Gone. So can someone tell me how can I make this a joke by doing that? Like if I touch something in the entire problem, how do I make it to be a joke of a problem? I just need to like touch it once somewhere. No. Except this one, right?
Yeah.
No. Come on, Calc 1. I know you're Calc 2. Come on, Calc 1. You suck. Because you have 81 plus x squared equals u. And you have your 2x up there, and it's just u squared on the bottom, you're done. So if I just kill this, it's a Calc 1 problem. Basic u sub. I put the square there, it's a trig sub. Such a cool problem, right? I mean, you might have a different definition of cool, but, you know, considering what I do, such a cool problem. All right, go. Do it. I'll give you some time. Do we have the same equations? So you either have this tangent secant pairing, or you have the cosecant cotangent. If you swapped x and a 9, there is no other way to do this. That's it. Those are the two. And I told you, if you end up with the secant, cosecant cotangent, all you need to do is to swap x and 9, and it will be secant tangent. The formulas are the same. It's just that it's negative signs, and you can make a mistake with that. So now, our dx, guys, is 9 secant squared theta d theta divided by, and if you look at the denominator, there is no square root, right? So how do I go from a square root to a square? Like, what are the exponents that I need to raise both sides? Yes, it's a 4. Because half times 4 is 2, and we need square, right? So you need to raise the square root equation, the blue one, 4 on each side, and then the square root will cancel with the 2, and the other 2 will stay. So what you are getting here is 9 secant theta to the 4, because this equation needs to be raised to the 4, and this needs to be raised to the 4. And I can actually write that algebra on the side. U to the 1/2 to the 4 is u squared. That's technically what we are using. Maybe I should put that orange. So u to the 1/2 raised to the 4 is u to the 4. Maybe not use, how about use y? Because now this u looks like a 4. There we go. So y to the 1/2, that's the square root of y, raised to the 4th is y squared. So we are replacing, and this is why you don't actually have to have a square root, right, in the problem for trig sub to kick in. So this tells you that certain integrals that you have done in the past, right, before you learn this, like trig sub can be used, right? And you just go. It's very easy to make a joke out of this problem if you just put an x over here. It's a u sub. But can you still do this with a trig sub? Yes, right? Because you have a value for x to sub in, right? So, but, you know, that would be overkill, like driving to RV over the Holland Tunnel. You know what I mean? You can do that every day, but why would you if there is a faster way right between where you live and here? Make sense? So, now you just have to deal with this nightmare, which is 1/9 cubed on the outside. And it's not a nightmare because it's secant squared divided by secant to the 4th. That's 1/secant squared. Huh? What 1/secant squared is? Yeah, cosine squared theta d theta, and here's your power reduction again, right? Kicks in. And we have pretty much the same solution as before, right? So 1/9 cubed, integral of 1 plus cosine 2 theta over 2 d theta. I just put 3 dots, and usually, as I say, I put this symbol. What does that mean? Just do it, exactly. When you get home. I need to go back a little bit to 7.3 because I see some hesitation, or maybe you didn't have time for homework and so on, you haven't done stuff. just to make sure that you understand that trigonometric derivatives and trigonometric integrals are paired. Sines always go with cosines. That's it. You cannot go out of that, out of those two as a pairing. Secant tangent, cosecant cotangent. And then these identities that link them to Pythagorean identities, right? They also fall in the same category. So going back, calc, trig, pairs.
You said this was 7-3.
Well, this is general calculus for trig.
I think that's actually where she was going to start. Now that
Yeah, we touched on 7.4, but it was like just one test.
No, we ended at 7.3.
Yeah.
We passed way at the end.
And so trig pairing, sine theta with cosine theta, secant theta with tangent theta, cosecant theta with cotangent theta. And this goes for derivatives, integrals, and Pythagorean identities of this sort. So this pairing is always observed. So if you ever get a sine cotangent pair, that something is really wrong there, right? You can't have sine cotangent pair because they're not compatible in any of the formulas that we have, right? Well, granted, sine is part of cotangent. Maybe you can, you know, do some magic there with u sub. But when you do the trig sub procedure, or you have the trig integrals given to you, they should always follow this trig pairing, right? So now you know that sine, derivative of sine is cosine, integral of sine is negative cosine. Derivative of cosine is negative sine, integral of cosine is positive sine, plus c. Derivative of tangent is secant squared, right? Derivative of cotangent is negative cosecant squared. So cotangent, cosecant, they always fall in this in this grouping. And when you study these things systematically, you should be able to understand quickly. I'm just gonna see if they gave those forms. They didn't. Too bad. But I can go to actually derivative of trigonometric functions. There we go. Because derivatives show integrals as well. Looking for the chart. There it is. Can't make it any bigger, but so you read from left to right, it's a derivative. You read from right to left is the integral, right? And then integral or derivative of tangent is not a basic, right? It's not a basic integral or derivative, because for derivative you're using quotient rule, sine over cosine, and for integral you're using the u sub to get ln for tangent and so on. So this is the basic stuff. And see sine, cosine, cosine, sine, tangent, secant, cotangent, cosecant, secant, secant, tangent, cosecant, cosecant, tangent. Okay? And all of the ones with the k are negative. That's the for derivative. Opposite for integrals. Ta-da! Right? Bye.